This will be lecture 2. We will talk about distances between points on a manifold and the shortest path connecting two widely spaced points. So you all know what a manifold is. It's some smooth surface which could be curved, could be flat, whatever. It can take very simple shapes. It can be a flat plane. It can be a circle, a sphere, a Mobius strip, a Klein bottle, whatever. But the point is that it's got to be smooth. So the thing that will characterize a manifold, at least locally, will be how you measure distances between two closely spaced points. So let's take one point which is over here, another point which is here, and let the coordinates of a point be denoted by x mu, where mu goes from 1, 2, all the way up till n. N is the dimension of the manifold. Okay, now on this manifold, there is a measure of distance which we will call the metric, G mu nu, where again mu and nu, they run from 1 up till n, and this will have the property that it is symmetric. If you flip mu and nu, that remains unchanged. The defining point, the distance between them, let S be the distance, and here I'm putting distance in quotes because there will be many different ways by which you can measure distance between two points. And since we are considering only a small patch, so of course the manifold M extends very widely, but we will consider 2 points that are very close to each other. So the distance, the small distance between them will really be what defines G mu nu. And what this means is, whenever you see a repeated index, it means you sum over mu going from 1 up till n, and this is called the Einstein summation convention. So let's say that example, for n equal to 2, we would have ds squared equals g11 dx1 squared plus g12 dx1 plus g21 dx2 dx1 plus g22 dx2 into dx2 squared. Now, of course, because g12 and g21 are the same and dx1, dx2 is the same as dx2, dx1, that means that, of course, these terms double up. But this is just to explain what the metric tensor, I use the word tensor, I should never use the word tensor without telling you what a tensor is. So cancel me, I just meant the metric. It is just 4 numbers in this case. It will be n squared numbers in the general case. Why we call it a tensor, you will get to know later. Okay, so What about, let's start with 2 dimensions, in which case ds squared will be G11. So let's look at flat, or what we call ordinary space for n equals to 2. Then ds squared is just dx1 squared plus dx2 squared. And that comes just Pythagoras. So then ds is equal to the square root of the separation between the 2 points. In 3 dimensions, you will have dx, you will add on dx3 squared. In n dimensions, you'll go there, and so there's absolutely no problem. Okay, now let's identify what G11, G12, G21, G22 are in this case. So look at this, then obviously G11 is equal to 1, G22 is equal to 1, G12 is the same as G21, which is 0. So here is a space where the metric is given to you. To repeat, 2 points that are separated by some small distance, the distance between them is ds squared equals this, and this is the defining thing. And from here, we'll be able to get how much is the distance between 2 points which are not infinitesimally separated, but by some large distance. Okay, so G mu nu was given to us by Pythagoras. In general, it will be given to us by God. But let's work out some other examples so that we understand where G mu nu comes from. Okay. So this was now before I go on, in what we will do today, it makes no difference whether I put the index up or I put the index down. But when we do general relativity, it will make all the difference in the world, whether it is up or down. So presently, what we have is x1 is x, x2 is y, and x3 is z, and so forth. Similarly, x1 is x, x2 is y, and so as I was saying, it makes no difference what is up or down. When something is up, this is called contravariant. When something is down, it is called covariant. And something like this, dx mu, again repeated indices, and that you all know is the Einstein summation convention. That is short for this, dx1 dx1 plus, and the last one being dxn dxn. Similarly, you see here, G mu nu is covariant. It's written in a covariant way. When it is up, then we can have G mu nu, and this will be called contravariant. So just names for now, but these names will be important when we come to space-time. If you're in just plain space, it's okay, but when you include time, time comes in with a negative signature, and that's where the difference between covariant and contravariant will be important. But for now, we're just going to do with plain space. Okay, so that's how we define distances in a flat space using Pythagoras' theorem. But let's come to a curved space, and the simplest curved space that you can think of is a circle. Okay, so we will, what is called S1, where we have x1, where we have, okay, let's just use x squared plus y squared is equal to r squared. And this over here is the radius of the circle fixed. Now, there's only one number that characterizes where you are on this manifold. So if you are here, well, then you can write x is equal to r cosine theta, y is equal to r sine theta, and then obviously dx is equal to minus r sine theta dy times d theta, of course, and dy will be r cosine theta d theta. There's only one degree of freedom. There's only one number which characterizes where you are on this manifold, and so we can write ds squared as r squared sine squared theta d theta squared plus r squared cos squared. And that's, of course, just r squared d theta squared. Fine, nothing unusual about it. And we will need this result, so I wrote it down. But what about when you go to something slightly more complicated? Let's go to a sphere in 3 dimensions, embedded in 3 dimensions, that is, but S2. So this is what's the difference over here? You have a third coordinate x squared plus y squared plus z squared equals r squared. And then you will need 2 coordinates, and that's why polar coordinates were invented, and polar coordinates are x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, z is equal to r cos theta. Okay, now I won't bore you with this thing. ds squared, you will take dx squared. Well, when you take dx squared, you have to differentiate sine theta, and then you also have to never mind. You know that there'll be sine theta d theta, and then cos theta d theta, and there'll be minus sine phi d phi. So 2 terms over here, 2 terms over here, 1 term over here. When you add them all up, you will get r squared d theta squared plus r squared sine squared theta d phi squared. And if you write this, this is r squared d theta squared plus sine squared theta d phi squared. And so, can you tell me what? So how should I now think of G mu nu? What is G mu nu? Now that I've given you the metric, can you tell me the elements of this metric? Yes, बताइए. Who will tell me here? R squared is outside. D theta. Huh? Okay, first of all, what do I mean? What is x1 here? What do I mean by x1 here? No. I mean a coordinate, right? X1 means what? Theta, exactly. X1 is theta, dx1 is d theta. And what is x2? Phi, absolutely. So I am now looking for the form d squared is equal to g theta theta d theta squared plus g phi phi d phi squared. And what happened to the d theta d phi terms? And what do you mean orthogonal? No. Okay, so if I was to do this calculation, I would see that the d theta d phi terms cancel out. And so g theta phi and g phi theta are both 0. So there are 4 numbers, g mu nu, but mu stands for theta or phi. And there are no cross terms because they cancelled out. When I, should I do this to Tigana? Okay, good. But can you see roughly why they cancel out? Okay, let's see. When I take dx, then this will be r cos theta d theta cos phi. Yes. But let's see. Then the other one will be plus r sine theta sine phi with a minus sign, because when you differentiate this, yeah. And dy will be very similar, but it will have a plus sign over here. When I square this and I square this, then the cross terms will go away, which is why this and this are 0. Okay, so now from here, what were you telling me? G theta theta is r squared, and G phi phi r squared sine squared theta. Good, that's all I need. Now, suppose I was to go to 4 dimensions. Then I would need polar coordinates in 4 dimensions. Do you think we can find polar coordinates in 4 dimensions? Yeah, all you do is add on another angle. So to locate in 1 dimension, so on a circle S1, you need only theta. In S2, you need theta phi. In S3, you will need theta phi alpha. And then you can go as long as you can with all the Greek alphabets you know. And if you run out of them, then you put 1, 2, 3, 4. And then you can go to an infinite dimensional sphere, S infinity, and you'll have polar coordinates for that. So no problem about them, all very simple. This we shall need, we shall record somewhere. Okay, but I also need another thing, which is G mu nu. What? I need to define this for you. So you remember that how was this defined? ds squared was defined as G mu nu dx mu dx mu. But how am I to define this? Let me give you the definition. This is the first time in your life that you are seeing this. And this is the Kronecker delta, which says that unless mu and rho are equal, this is 0. It is 1 if this and this are 1. So, in a sense, this is matrix multiplication, isn't it? There's the common index nu which is being summed over. And yesterday, what you heard about multiplying matrices, well, this is one matrix multiplying another matrix, and this has to be the unit matrix. So therefore, this is the inverse of this, or you could say this is the inverse of that. So that'll, looking at this, can you tell me what the elements g theta theta will be? 1 by r squared. And what will g phi phi? And you have to tell me everything. This will be, has to be 0. Let's check this. Okay, that's 4 numbers to check, but let's check one of them. Let's take g theta nu g nu theta, let's say. Okay, I'm summing over nu, but this is diagonal, so unless nu is equal to theta, this will be 0. And so if nu is equal to theta, this is 1 over r squared, this is r squared, so the answer is 1, as it should be. What if I take phi over here? Huh. क्या चीज? हमने ये हाँ no this is the definition. It has to be. So no, I'm not saying no. I'm not saying g mu nu is equal to 1 over g mu nu. No. I'm not saying that. I'm just saying that when you multiply these two matrices together, you should get the unit matrix. So therefore, we can complete this over here. This is equal to, well, if nu is equal to phi, then this is 0 and this is 1 r squared. Yeah. And so this is equal to 0. So there are 4 numbers to check over here, and they all check out. Yeah.
So, sir, like to get a basic idea of what we're doing exactly here is in a manifold, when you zoom in enough.
Can you use the microphone? Yeah. Yeah.
Achha, so hello.
Yes. It is working. It is working.
Okay.
Yeah.
Achha, so to get a basic idea here, when we look at a manifold, if we zoom in enough, then at infinity you could say Euclid's laws do work, right?
No. Please don't talk about infinities. All I'm doing is looking at a very small piece of the manifold. Remember, we're doing differential geometry.
Yes.
Differential means difference between two very small.
Yes, I was getting to that. So at that small patch, we can measure the small distance ds using the dimensions dx, dy, dz.
Using this, ds squared equals. So this is really where everything starts from. 2 points. This is x mu. This is x mu plus dx mu. So, of course, there can be n numbers over here. There will be n numbers here. There will be n numbers, coordinates here. And the separation between them is obtained by this formula. Now, what's your question? So
then we put that, put the distance, put all of that into the matrix tensor and metric tensor, and the metric tensor is what basically gives you the whole distance when you multiply it, right?
In this case, we are basically using Pythagoras' theorem.
Yes. Yeah. At like a very differentials ko use karke.
Yeah. So we will simply say that we know what the distance between 2 points on the manifold separated by a small distance. Distance means theta is small. In the case of the sphere, phi is small, d phi. This is small. I didn't mean that theta is small. I meant that the difference in theta between the 2 points is small.
Yes.
Yeah.
Okay, theek.
Okay. Question over there.
Sir, I have 2 questions. A little while ago, you said it doesn't matter if the index is in the superscript or the subscript, but over here there is a difference if it's up or down. So, why?
Thank you very much. That's a good question. I said for the coordinates. So, x1 is theta, x2 is phi, x1 is theta, x2 is phi. So no difference over here, but I didn't say that the metric tensors, metric would be different.
Second question, so I understand the mathematical definition of what the metric is supposed to be. Can you explain, so you're saying that we're basically doing Pythagoras in like an advanced way. So what does the metric signify, I guess, over here?
Okay, so if you take a circle, we found ds squared was r squared d theta squared. When we took S1, that gave us that. When we took S2, ds squared was r squared. I don't want to write this whole thing over here. I'll call this d omega squared, because this is what you call the solid angle. Yeah. So this is d omega squared. And if I was to write Sn, that would be ds squared equals r squared d omega. This will be a different solid angle because you're living in n dimension. Okay, so this is not a okay, so underneath there is the Cartesian coordinate system, because we went from the Cartesian to the curved manifold, but there we had a constraint. The constraint was that every point has to obey this, or it has to obey x squared plus y squared equals r squared, and generalized to n dimensions. So in this way we were able to get the metric. But as we will see in general relativity, the metric will be obtained from elsewhere. It'll be obtained from Einstein's equations. So for now, we are not concerned about where the metric came from. You are given a metric, and now what we want to do is find the distance between 2 points.
So there's no physical meaning.
There's a lot of physical meaning.
So तो वो पूछ रहा था यानी मतलब ये पूछ रहा था कि उसका physical meaning क्या होगा फिर?
Well, I gave you the physical meaning. Do you know what distance is? What is it?
The distance.
What is the distance?
Separation of 2 points.
Yeah, okay. And what is it? It's actually this. We define the distance as being this. And look, in relativity, we will see that a ray of light travels on the path where the distance, where ds squared is 0. Always 0. Wherever light goes, ds squared is 0. So how you define distance is absolutely crucial. It's our starting point, absolute starting point. We are given the metric, and now we have a long way to go. So we shall proceed.
Sir, one more question.
Yeah.
Acha, so just to visualize, let's talk about Euclidean space and what the metric would be there. I think it would be like dx square, the metric would be like 1 0 0 1 in like Euclidean 2D space on a flat surface, right?
Yeah. It not 1 0 0. It'll be
It
the
will be
unit
like-
matrix. It'll be so.
It
G
will be like the
mu
identity matrix.
Yeah, it'll be 1 1 1 1. All other zeros. In 4 dimensions, it'll be this. In n dimensions, it'll be all.
So
ones.
can we think of the metric as like telling us what coefficients we put next to terms?
So look, in 2-dimensional space, as we saw, ds squared is dx squared plus dy squared.
Yes.
3 dimensions is dx squared plus dy squared plus dz squared, etc., etc. And the g's are 1 1 1, except when mu is not equal to nu, when it's 0.
Okay, so another, like, just to visualize it better, if we were to replace this with a metric where it was just a diagonal matrix with 2 2 2 2, then its physical representation would be like a distance in this manifold is double that of the other one.
I don't know what you mean by that, but here is what, if you use the word matrix, so this same equation I
Yes.
will write as let's do 2 dimensions. So you like it better this way?
Yes.
All right. So whatever you like, I like. Anything else? Huh.
You can just correct me. So when we go from one coordinate system to the other coordinate system, we have a transformation metric that comes with it. And this G is basically that transformation. When you write from XY to theta phi, then how we transform from one coordinate to the other, the distance, then this transformation metric comes with it. That you call the matrix.
That is perfectly fine. So I could have written ds squared in two different ways. I could have written it as, let's take S1 again. That's one way of writing ds squared. This is another way of writing ds squared. Now here the thing is that x squared plus y squared has to equal to r squared. And here there is no constraint.
I think the question that earlier he had was about the sort of physical significance. So one could say that it is something that is specific to a manifold that tells you how the distance is related to the dx1, dx mu or dx nu.
Yeah,
The
to the coordinates.
that you
Yeah.
take to
Yeah.
the coordinates. So
Yeah.
it's a quantity that is manifold specific, which gives you the relation between the distance and the coordinates.
Yeah, yeah, that's, yeah.
Sir, so can we simply say that as we have defined it for locally, so can we say that on a plane surface, when we move in a plane surface, the metric does not change. So we do not have difference in distance in a flat surface, and that's why our transformation metric is an identity metric.
Exactly. Thank you very much for saying that. That is what gives you the identity matrix. In flat space, the metric does not depend upon position. Here, it obviously does depend upon position. Where did that go? Yeah, here. G phi phi depends upon the value of the coordinate. Whereas here, they are all the same. Okay, so again, we come back to this. This is ds squared. By definition, the distance between 2 points. But I want to now move on my manifold from here along some path to here. Let's say this is A to B. And so far, I've only told you about what is the distance between two very, very close points. So what should I do to get the total distance? Add up the little pieces. So the total distance between 2 points will be integral ds. Integration is just summation, isn't it? That's all that it is. Okay, so let me put that in. ds is square root of this g mu nu dx mu dx mu. Looks a little odd, doesn't it? Well, now I will say, imagine that you're walking along from here to here. You can't go straight because otherwise you will go off the manifold. So you have a little, you have your wristwatch and you say, after 1 second I'm here, 1 second here, one here, and after 1 hour I come to my final point. Okay, so you have something that measures your progress along this path, and that is called Let's give that a name, lambda. And each little step you take is that of an increase in that parameter lambda. So what I'll do is I'll divide this by that small amount, and then I'll multiply by that. And so I've done nothing then. Lambda is what is called affine parameter. Now you hear this word affine and fear runs through you. What is this? I've never heard of this before. And I actually looked up the dictionary and it doesn't tell me very much. Call it anything you like. But you see, the thing about this is that I can multiply lambda by 20, but I will then divide over here by 20. Remember, there is a square root over here. Very important. So lambda can be scaled as you like. It can be made shorter, bigger. And when we do relativity, this is what will be called proper time. Okay, so what we need to do then, we need to minimize S. Now this square root over here is, you don't like it very much. And so I wish the square root was not there. And well, if I'm going to minimize this, why don't I minimize its square? Because if the square is small, the thing itself will be small. So let me define something called L, which is G mu nu x mu d lambda dx nu d lambda. And well, if I'm going to be minimizing this, what's the harm if I put a half over here and make this a definition? Okay, now I don't like writing this all the time, d by d lambda, so I will make a definition that this is x mu dot x nu dot, where dot means dx mu by d lambda. By the way, I can choose my lambda in a different way also. I could take it as the length along the path. So let's say this, since I can use any parameter lambda, and you see the lambdas I divided and multiplied by the same number. So can I not take lambda equals S? Can be is a possible choice as well. I may want to do it, I may not want to do it, but it's a choice. It's there because it's like A over A is always 1, and doesn't matter what the value of A is. Fine. If I sometimes say that this is a Lagrangian, please ignore me. I have simply defined this. This is a definition of half G mu nu x mu dot x nu dot. Okay, so So the task before us. We have S equals integral d lambda L. And where does lambda go from? Lambda starts from here at some value. You could call it 0. And ends here, you could call that 1. It doesn't matter. Whatever the starting value is to the final value here. And L is a function of x and x dot. So I could put over here mu and over here mu also. It's understood that, okay, L is really a function of x1, x2, and then function of x1 dot, x2 dot. So that's what this over here means. This x is now standing for a whole collection of positions, and x dots a whole collection of speeds. I say speed because speed, what is speed? What is velocity? It's the derivative with respect to something, right? It's a dx mu by dt, dx mu by d lambda, call it speed, first derivative. So L depends on the path and the speed on that path and the velocity on that path. And now this is going to lead us to the most important thing that you will learn in physics. It's called the calculus of variations. Yeah.
Shouldn't it be like the root of L?
So let's come back to this. What I need to do is to minimize this. But if I minimize the square, then I'm also minimizing this, and I don't like dealing with square roots. I could, there's no problem, but it'll just, okay, so look, it's like this, d by dx of square root of x. That's half x to the minus half. Yeah.
But then
I-
it should be s squared, right? It should be n squared. The definition of L
Yeah.
have a square.
So this is a quantity I want to be as small as possible. Then what about its square? I want that to be as small as possible. So it's the same thing if I do this or do that. But that is much more convenient. It's not exactly the same as this, but that is something.
It's an approximation.
No, it's not an approximation. It's something it's something completely, totally rigorous. There's no approximation. There's a function. I want its minimum value. I get something. There's a function. I want the square of that minimum value. Well, I can look at the function or I can look at its square. Same thing.
I don't understand.
Give.
So I don't understand how the x dot over here is velocity, because aren't we taking the derivative with respect to space?
No, with
We
respect
de-
to
we
lambda.
we define lambda as s, which is space.
No, that's a parameter. It's not a coordinate. This is a parameter. So as I walk from here to here, lambda keeps increasing from this value up till that value. So I start from 0, I end up at 1 or whatever.
But dimensionally, if we're saying lambda is equal to s and s has the dimensions of distance, then dimensionally shouldn't lambda also have the dimensions of distance?
Well, everything gets cancelled out because then whatever dimension lambda is, it gets cancelled out by here.
Fine, then shouldn't the derivative with respect to it be
So,
with respect to space?
whatever lambda is, well, we can choose lambda to be dimensionless, right? Or we can choose it to have dimension time. Whatever you want, I am going to call this I'm going to call this the velocity. In fact, the velocity vector. Velocity doesn't always have to be with respect to time. It can be with respect to something else. It's just a different name. Okay, you don't like velocity? I'll say it depends on the path and on the first derivatives of that path.
Rate is still with respect to time.
No, there's no time. There's no time. I assure you, there's no time at all. It's a number. Any number that is different. So, lambda can be time, but lambda can also be the distance along the path. It's just something that has to keep increasing as you walk along to the final destination. What else could it be? Use your imagination. Mike.
So you mean we're just minimizing this term? It could be anything, like it could be with respect to time or it could be with respect to space. We are
Space, no, with respect to that parameter.
yeah, and that parameter could be anything depending on the context or the situation we are in.
Yeah.
We are just picking the path that has minimum of this value.
Yeah.
Okay.
So now here is the real problem. I want to go from here to here, and let's say that this is the path which is shortest, which gives me the smallest value of S. This is what will be called the geodesic. And how do I find this geodesic? Well, I am reminded by the question in calculus, how do you find the minimum of a function? So remember that when you learned calculus, you were given a function and you were asked to find its minimum. Well, you say, aha, this is where the minimum is, just visually looking at it. What does that mean? You go a little bit to the left or a little bit to the right and the function does not change to first order. That's what the derivative means. Go a little bit here, a little bit there, no change. On the other hand, if you are over here, you go a little bit here, oh, function goes up. Go a little bit there, oh, function goes down. Huge change in the function. So to first order in the shift, there should be no change in the value of the function. Do you agree with me? Is this what you learnt in calculus? You did. All right. Now I want you to tell me, in this case, how am I to find the minimum value of S? This is something which is given. How am I to know the minimum value? How am I to know that this path is the true path? Just think of how you did it when learning calculus. What will you do similarly here? Bataiye.
A path that is a little bit different.
Very nice. And then compare it with the true path. Okay. Good. Oh, I didn't mean to. In fact, what you're telling me is the following. I need to go from here to here. This is the true path. But I need to then explore a path that is close to it, or maybe a path that looks. So I need to explore all paths which are close to the true path. So then what do? I use calculus. So what you will learn now goes far beyond differential geometry. It is something that you will see in mechanics. You'll see in optimization theory. You'll see in artificial intelligence and everything that there is. So let me do the following. Let me take S, which depends upon, so let me take S, what should I call this? S0 is the true path, or let me call it SC. SC is the actual value of is the minimum value of SC. Then this is equal to and now L depends upon X. What I've done is I've now taken a different path, so that path is X plus something small. And I've also shifted this. And now I need to subtract from this the clear? So I've evaluated S a little away from the best value. This is how I will find the best value. Okay, so then the rest is, okay, this is d lambda. And now let's see how this works out. If I have shifted this by a small amount delta x, then this is dl by dx, and this is evaluated at x equals xc delta x plus how, I see L depends upon x dot as well. Oh, sorry. I should have. I should have done this. This is now I'm so. You remember the Taylor series? If I have f of x, well, that's f at into x minus xc. how much you have moved away, and this is what we call delta x. So I have L at xc plus dl by dx delta x plus dl by dx dot delta x dot minus and of course I ignore terms of order delta x squared and all that goes away. And so what is this and this? And I'm left with this. Any question on this? Because no question, completely clear. Okay. So then this is dl by dx dot delta x and delta x dot is this thing, d by dt delta x. Agreed? That's what. I'm going to rewrite that last term. So that last term I'm going to write as d by dt So I'm going to say that this is the last term. And did I miss something? Yeah. Delta x. Yeah. So is this correct?
Only with t you have to write lambda because the parameter is
Well, oh, yes. Here. Yes. Yeah. Yeah. And where else? That's it. Either. Yeah. आदत खराब हो जाती है ना. From classical mechanics where you use T all the time. Here we're using lambda. So then, that's simply the chain rule over there. Okay, so now we are having, so then I have delta S, which is this thing, the shift delta S is equal to then this thing, d lambda, and I write the first term here, dl by dx minus d by d lambda delta x minus d by d lambda of this thing. In fact, let me do this. Let me write this as minus d lambda So now we are in very good shape. And where do the integrations go from? They go from the starting point, lambda a till lambda b, lambda a to lambda b. Now look at this diagram over here. We were told to start from this point and end at this point, and to explore all possible paths that start here. Start here means delta x has to equal to 0 over here, and delta x has to equals 0 over here. And now, what does the fundamental theorem of calculus tell you over here? What is the fundamental theorem of calculus? It's that if I have dx, d by dx of f of x from x goes to a to b, what is this equal to? F of b minus f of a. So the value of the function at the top minus the value of the function at the bottom, but delta x is 0 at the top, delta x is 0 at the bottom, and so done with this. That is 0. Now, delta s was the small shift in s when we went from one path to the other, and it has to be 0. Now the only way for delta s equal to 0, when I say 0, I don't mean 0, I mean 0 plus order delta x squared. Whatever terms there are have been thrown away. Those are of higher order, and we don't care about them because we can make that smaller and smaller. That's our choice. And so delta s has to be 0, which means that we get dl by dx. Let me put it this way. Which means that whatever is here has to be 0. So d by d lambda of dl by dx dot minus dl by dx has to equal to 0. And this is what is called Lagrange's equation. So and this is extremely, extremely important in every branch of physics. Let's have a discussion on this if there's anything here that you did not understand, because it's so very important. Yeah. Mike Lynn.
So I'm confused in the first step there. There was a plus sign on the right side of board, right?
Where?
In the last equation.
Here? Here. Okay, so this has to be 0. So I could make this plus and this minus.
So in the last equation on the right side.
Here?
Yes. There was a plus sign there.
There is a plus sign.
Yes.
Yes. So what I did was I took d by d lambda out over here and applied it, and then so I use this thing.
Yeah, but don't we have plus sign in product rule?
Okay. Okay. If you find it easier, take this. This over here, just differentiate this. D by d lambda will first act on this dl by dx dot, leaving this as it is. So that will cut that out. There will be one remaining term which will be d by d lambda acts on this, which gives you delta x dot.
Okay. Then there would be d by d lambda of delta x, not delta x dot. On the left side of the first equation.
See this delta x, so d by d lambda of this is what we call delta x dot.
On the left side.
Can someone come, because I am having difficulty understanding this. Huh. Huh. Aha, yeah. Oh, okay. Thank you. See, this is what I cannot see from too close. Are we done on that? Yes. And now he's. This is so important. I have to write this down again. No, I won't. But just look at it. If your mother wakes you up at midnight and asks you to write down Lagrange's equation, you should remember that. Okay.
It should be 3 p.m. These guys are at midnight.
Okay.
3 a.m. Sorry.
Okay. And now here is. Now we're going to apply this. So L is half what is dl by dx mu? X mu dot, let's take this. Okay, what will it? Okay, now no, that's not a good way. That's not a good question for me to ask. Why? Because mu is already used up. It's a dummy index over here. So I can ask this question: what is dl by dx1 dot, or 2 dot, or 3 dot, all the way up till n dots, but I cannot use the symbol mu because that's already used up. So instead I will ask, what is this? Okay, so G mu nu does not depend upon velocities. It only depends upon positions. Very, very important to understand that this is independent of that. So when we looked at Euclidean geometry, this was just constants, numbers. When we looked at S1, S2, in S2, it depended upon theta. So it depends on the coordinates, but not on the velocities, not on theta dot. So what will this be? This will be half G mu. So d by d, so this since we are doing this for the first time, I will do it in a very do it with complete detail. Now these here, these are independent of each other. So unless mu is equal to rho, this is going to be 0. In other words, you could say this is a Kronecker delta. Similarly here, unless nu is equal to rho over here, this will be 0. So here we have half g rho nu x dot nu plus half g. And what will I have over here? Nu has to equal to rho. See this? These are independent functions, and so unless nu is equal to rho, we're going to have 0 over there, and so we have mu rho x dot mu. We have two things that look very similar, and in fact, this is a dummy variable, so I'm going to simply give it a new name. I'm going to call nu mu. And now this is g rho mu, and this is g mu rho. So this whole thing is simply g mu rho x dot mu. Take? All right. Let's write down our result over here because it's going to get, so we have dl by d and now notice one thing, the mu has been eaten up. It was a dummy index, and rho remains on this side, and rho remains on this side. Okay, that's one result. So remember that this over here is holds for all x. So I could put over here mu. I could put over here anything, rho.
Sir, wouldn't the second variable always be 0 over here? Because in our definition of L, there's no x rho, there's only x dot.
Good point. Good point. Let me just go to the next stage, and then you'll see exactly what's going on. Okay. The next thing I need is dl dx rho, with L being this. And now, just as you pointed out, this doesn't contain x, this doesn't contain x, is position and velocity. If you know the position, that doesn't mean you know the velocity. If a car is here, I tell you it's outside the black hole. Well, did I also tell you how fast it was moving? I didn't. So x and x dot are completely independent of each other, and hence your question, what do I do now? Well, I do know that this depends upon Yes? And you will agree that G mu nu does depend upon position. We saw that explicitly. It depends upon theta, for example. But now I can use the chain rule. So this is d by d lambda of dx rho right? Chain rule. Chain rule says क्या चीज?
Instead of partial g, it should be d lambda.
Here?
No, in the numerator of the second fraction.
Can you come here and show me what you mean?
Shouldn't this term be d lambda?
Oh wait. No wait. I've done something wrong. Wait. This. Wait a minute. This is fine actually. I don't need to do anything. This is fine. I don't need to do anything more with this. This is fine. Okay. Sorry about that. Okay. So then let me now put this into dl by dx dot rho. Just a second now. Okay, that's fine. Okay. So now I have d by d lambda of this. Minus this. Okay. Everybody agreed on that? That I've just put in dl by dx dot rho from here, and I have dl by dx rho I've written here. And now we are very close. So this is d by dl of g mu rho acting on this alone, x dot mu plus, now it has to act on this. So what do I call that? Double dot minus half right now here I'm going to write this as dx, what should I call it, nu? Now I'm going to use the chain rule. Are you okay with that? No problems. I used the chain rule too early and wrongly. Now I'm doing it right. So then let's gather all things together. What is this thing over here? This thing is x nu dot. So then I have g mu rho x mu double dot plus d g mu rho by dx nu from here. X dot mu, x dot nu. This thing is x dot nu, which is here, minus half dg mu nu by dx rho x dot mu x dot mu. And this is equal to 0. So this is Lagrange's equation, and we are almost done, except that, you know, this is, see, this is symmetric in mu nu, and this is, does not look symmetric in mu nu, but it actually is, because I can call mu nu and nu mu over here. So I can actually break this in the following way. G mu rho x double dot mu plus half So what I've done is I've written it half this way and half with mu and nu. And that's equal to 0. So 0 is equal to this. And now one last thing that I need to do is, if I have something equal to 0, I can multiply it by anything I want. What do you think I should multiply in order to give this a nicer? Very nice, very nice. So I should multiply it with the inverse of this. So I am going to multiply by G sigma mu. I'm going to multiply both sides of this like this. If 0 is equal to, if I multiply 0 by anything, it's still 0. So that's, which then gives us our एक मिनट there is a problem, yes. Mu, wait, this has mu rho nu, where is the problem?
सर जिस मैट्रिक के साथ मल्टीप्लाई किया है उसमें म्यू नहीं होना चाहिए क्योंकि
एक मिनट जिसको मैंने, so what I need to do is have a mu and a sigma and a mu, let's put it this way. No, I can't do that either. Sigma and rho. Yeah. Yeah. So now rho and rho will sum with each other. Sigma is new, so it's not been used anywhere else before. And so immediately I get the final shape of our equation, which is x double dot mu plus half. Acha. You see what has happened over here? Rho and rho, this gives you delta sigma mu. So then this becomes sigma. And then let's see what happens over here. Plus half. This thing is given the symbol sigma mu. It's called the Christoffel symbol. So this equal to 0, x, kya?
X dot mu, x dot mu. Square bracket for now. Outside the square bracket.
So this thing over here up till here. So the final form is this is called the geodesic equation. If you solve it, you have found the path that minimizes the distance between 2 points. Success. We're over time, but give me 1 minute more. There are derivatives of the metric over here. What if the metric is flat? What if it doesn't depend upon x? Then it's 0. So this is 0, this is 0, this is 0, which means x double dot sigma is equal to 0. And who will tell me the solution of that? Give me the solution. What is the solution of this? X sigma is equal to what? Something times which carries the index, let's say it's some constant times plus some other constant, whatever, plus constant. This is the equation of a straight line. And we have found that in flat space, a straight line is the shortest distance between 2 points. This is like कान यूं पकड़ने वाली बात है, but that emerges from this. Good, and then next time we will explore this further, and this then will lead us into tensors, into curvature, into other things. Any question, anything that's bothering you? I hope, there is all this manipulation over here, which all this is in the notes. So you can work this out by yourself, and you should. Working with dummy indices is sometimes a little tricky. You can call mu new, sometimes you call new rho. You keep switching as you like. And also this tells you that indices you can sometimes get confused. And it would be so good to have geometry without indices. But that takes a lot of abstraction. This is very ground level stuff. Yeah.
So we didn't define the lambda to be S or T yet, right? So can we say that this is the shortest or fastest path because we don't know what the lambda is?
Okay. So when, okay, good point. So if you take the affine parameter to be time,
Yes.
you'll say it is the shortest in time.
Yes.
सबसे जल्दी हम इस तरह पहुंचेंगे.
Yes.
If you take lambda to be the distance, then this is shortest in terms of distance.
Yes. So it could
Or
either
suppose it costs money to go from. This is the path on which I will pay the least amount of fare to Yango. You see, it depends on what is the cost function. Now, a Yango from here to Apara can go multiple ways, and it will be different for a motorbike. So each has its own cost function. And in general relativity, that depends on the metric of your space. Okay.
लेकिन आप कहते हैं कि लैम्डा एक डायमेंशनलेस क्वांटिटी भी हो सकती है, तो स्पेस टाइम के अलावा कोई और
I didn't say that. I didn't say that it has to be, because you see, when I did this, I started with this, and then I said, now it doesn't matter what lambda is.
Yes.
Whatever it is, it will cancel out.